in the US. Nuclear power is not the same as it was in Chernobyl. It's not the same as it was when it came. And we classified nuclear generation processes by generations. So we're probably at the moment between generation 2 and generation 3. And generation 3 are the reactors that people are now considering to install. There has been a break, really. Generation 2 reactors are the ones that have been operating, and some of them are coming to the end of their life. But people are talking about generation 4. And generation 4, I guess, is the more blue sky. And the goals for generation 4 nuclear systems, because it's blue sky, because it's still research and development, you can really look to what you want. You want sustainability. You want good economics. You want safety and reliability. And you want proliferation resistance and physical protection. So you want to have processes or systems or fuel cycles that don't produce plutonium. That any plutonium that's produced in the reactor is used in the reactor at the same time. So you design the fuel to do that. And it's very difficult, for example, to get the fuel out and get any nuclear material out of it. Well, how about come back to home? Well, I think nuclear does offer an alternative for low emission. The cost per megawatt hour is acceptable. It's in the ballpark of the others. However, entry, and I think Tony will be talking about this later, entry requires a big investment. It requires coordinated infrastructure, and Australia hasn't got that in place. What about, as the other thing for Australia, what's the timescale for community readiness? And being a researcher, of course, I've got to end by saying, for Australia, maybe countries like Australia should also participate in these long-term international development programs. Not just Generation 4, but fusion, and Andrew's going to tell you about that. Thank you.
So let's move right along to the first respondent, Professor Andrew Cheetham, who is the Pro-Vice-Chancellor of Research at the University of Western Sydney. Andrew has a PhD in plasma physics and spent 15 years working in the field of plasma diagnostic systems in nuclear fusion, energy research which took him to laboratories in Germany, Switzerland and the United Kingdom. He returned to Australia in 1990 and has been at, I think, UWS, Andrews, 2 years, 18 months, as the Pro-Vice-Chancellor. He's a Fellow of the Australian Institute of Physics, a Fellow of the Institution of Engineers Australia, and a Fellow of the Alexander von Humboldt Foundation, a member of various boards, and is very widely published. So, Andrew, to talk about nuclear fusion.
Good evening, ladies and gentlemen. I got a very good segue there from George. He mentioned fusion right at the end and in the middle, but I do feel a bit like the lady in waiting, as it were, because this is all about research. None of this actually works yet. Well, it works, but there's no reactors been built. And George's last date up there was 2050, and that's about when the current estimates are that the first nuclear fusion reactor might be built, or rather might be commissioned. What I'm going to talk about then is nuclear fusion energy, how it works, why we think it's more advantageous and better for our future, what are the challenges, both scientific and technical, and there are some quite big ones, that we need to overcome to get it to work, and then finally what the international community is actually doing at the moment. So how do we make this work? The atoms fuse together. Well, it's easy to say that. In fact, I just did. But to make it happen requires a little bit more effort. You actually heat the hydrogen. It starts off as a solid at absolute zero at about 14 Kelvin, which is like minus 250 something, 60 something. It turns into a liquid. Doesn't like being a liquid much. By 20, it turns into a gas. Stays a gas until about 160,000 Kelvin, where it turns into a plasma. And what that means is you've ripped all of the electrons off of the atoms, well, the electron in that case. Now, that happens at around about 100 million degrees is what we need to get our fusion reactors to go. And that means that the atoms are moving so fast that they will actually stick together when they hit each other. And you might say, why? Because they're both positively charged. Why aren't they just pushing each other apart? And you could ask that question about the nuclei in your body. They all are made up of protons and neutrons. Protons are positively charged. Why don't they fly apart? Because like charges repel. The reason is the electrostatic repulsion is a very powerful force, but it's long range. It's taken over by the nuclear force, which is even more powerful, much more powerful, but it is extremely short range. So once you get them to close enough together with momentum, then wacko, they stick together and you get the fusion reaction to occur. And that's what we have illustrated here. That brings up a few little challenges that come into play. First of all, you've got to heat the plasma. Secondly, you've got to put it in something at 100 million degrees. It's not going to be a glass bottle. And thirdly, the behaviour of such a thing is extremely complicated. As I mentioned, the plasma is a sea, if you like, a liquid made up of electrons and positively charged ions, so they are electrostatic. It is actually a gas, so it's hydrodynamic. So it obeys all of the equations, the many equations to do with liquids and gases to describe their behaviour, but it also obeys all of Maxwell's equations for electromagnetic effects. So you have got a highly complex plasma, very difficult to model, very difficult to understand how it works. The last thing is that once you've got it in that state, you've actually got to get it up to ignition. And ignition means you heat it and heat it and heat it. Once it's going, it starts to produce energy, and that energy can heat it further to keep the reaction going. It's a bit like lighting a fire at home. I live at Wentworth Falls, so we do light fires from time to time. Bloody cold up there. You put a match to the fire, and if you've got enough of the three magic ingredients, temperature, density, and time, and the time is how long the energy actually stays there, then it will start to burn and it will ignite, and you can take the match away. And so the key is, when can we take the match away from the fusion to let it go, i.e. it's reached ignition. And that can be, that has not yet been achieved. And we'll talk about that in a moment. Okay, so what would a reactor look like? Well, this is entirely schematic. Here's the plasma reacting away, and here's the lithium blanket that I talked about. So you have lithium into the blanket here, you have deuterium going into the plasma, you have tritium going into the plasma, and in there you form helium and deuterium, which get removed from the plasma. The neutrons come out and heat the lithium. You have a heat exchanger, which operates around here, and then you're back to the standard steam turbine technology, which we know and love. The deuterium and tritium gets processed. The helium is useful industrially. You may not know this, but helium is not manufactured. It's actually mined in Canada mostly, and we are actually running out of helium. So it'll be good to be able to make some for those industries that need it. So that is how a hot fusion plant would work. And what are the advantages then? The advantages are effectively that you've got sustainable baseload power. So baseload power system, you won't be making little small fusion reactors. You're not going to have watches powered by tokamaks. This is baseload power, and about the same output as a standard power station. The reactor is fail-safe. This is not a chain reaction, remember. If something goes wrong, then it goes out. In fact, you could argue we're having so much trouble to getting it to work that it will never be a problem of it going out. The radioactive fuel is recycled within the plant, and that is the tritium. It doesn't come out. You have to have a base load of tritium, goes in, and then it gets recycled. There is no long-lived radioactive ash. There is, of course, an irradiated structure, just like there would be in any nuclear plant, but those are not long-lived, and they're not difficult to treat, and also it only really is an issue at the end of the life of the reactor. There is virtually unlimited fuel. Deuterium is in seawater, and lithium is abundant in the Earth's crust, so there's not really a difficulty there, enough for thousands of years of fusion power. Lithium is the tricky part. But I haven't talked about the next step in fusion reaction, which doesn't require lithium, and I don't have time to. There is no operational greenhouse gas emissions, which makes it very useful. Operational because, of course, again, like with a nuclear power station, you will have some in terms of building the power station, in terms of extracting the fuel, and so on. And there are no geopolitical problems. This does not have any weapons potential.